Hello and welcome to a new topic in our course. So you have all seen family trees. They are things that look like this. So you have some ancestor who has some descendants and so on and so forth. And this kind of graphs called trees constitutes a very important family of graphs that has lots of applications. Not only family trees, but also trees describing genetic diversification or chemical molecules or trees giving an algorithm to search databases and so on. So they are worth looking at, and the mathematics behind them is, if I may say so, beautiful. So let's look at what is a tree. A tree is quite simply a connected graph with no cycle. So, for example, a path is a kind of tree because it's connected and has no cycles. Another example is something like this, a kind of a star, or the usual family tree style tree that you just saw. Such a graph is called a tree. So from the definition, it follows that trees are simple graphs, because if in a graph you have a multiple edge, then you have a cycle, and if you have a loop, then you also have a cycle. So automatically trees are simple graphs. And if you have a graph that is not connected but still doesn't contain any cycles, it's going to look roughly like this. So you have a bunch of trees and your graph is the union of these trees, and quite naturally such a graph is called a forest. One feature that trees have is that this no cycle condition means that they cannot have too many edges, and the connectedness means that they cannot have too few edges. In fact, perhaps surprisingly, we can prove that any tree has precisely one edge less than the number of vertices. So a tree on n vertices has precisely n minus 1 edges. The slogan is one edge less, or one edge fewer. How do we prove such a thing? Well, we prove it by induction on the number of vertices. So if you have a graph or a tree with one vertex, then since it cannot have any cycles, it must be just a vertex with no edges, so it has 0 edges, and indeed 0 equals 1 minus 1. Now let us prove this for bigger n, assuming that we have proved this for smaller numbers of vertices. So this is the induction step. So given a tree with n edges, remove one edge. So this should be edges. Remove one edge. Well, if you remove one edge, the resulting graph is disconnected. Why is that? Because if by removing an edge, say this edge between vertices v and w, your graph is still connected, this means that there is some other path between v and w. Because connected means that there is a path between any two distinct vertices. But if there is another path, that means that altogether you have a cycle. Therefore, removing any edge of a tree gives you a disconnected graph. Now, since you only removed one edge, the new graph will have two components. An edge just has two endpoints. So by removing an edge, if you're disconnecting the graph, it cannot have 3 or 4 or more components. It has two connected components. So once you have removed the edge, you have your two components, and each of these components is a tree with less than n vertices. So why is it a tree? Well, each component is by definition connected, and since the original graph had no cycles, definitely removing an edge will not create any cycles. So your components will be connected graphs without cycles, in other words, trees. And they will have less than n vertices because you have split the graph in two components, and the graph from the beginning had n vertices, So with two components with at least one vertex each component will have less than n vertices. So now we have trees with less than n vertices, and therefore we can use the induction hypothesis. It says that in each such component, the number of edges equals to the number of vertices minus 1. But now, since we have two components, in each of them there will be one edge less than the number of vertices. Then, since we have two components, in total we have two edges less than the number of vertices. So since the original graph minus an edge has n vertices, because we just removed one edge and didn't remove any vertices, we now know that removing this edge gives us a graph with n minus 2 edges. But then, of course, this means that if we had not removed the edge, in other words, in the original graph, there are precisely n minus 1 edges, which was what we wanted to prove. Using this theorem, we can say something about leaves in a tree. So the terminology about trees is kind of, well, inspired by the fact that we're calling them trees, so it's very forestry. But a leaf is a vertex of degree 1, or an end vertex. So if you have a tree that maybe looks like this, then in this case you have 1, 2, 3, 4 leaves. And a consequence of the previous theorem tells us that each tree with at least two vertices has at least two leaves. So you can have many more than two leaves, but at least two leaves. Why is that? Well, you have a tree with n vertices, so by the previous theorem it had n minus 1 edges. And so the sum of all degrees, because each edge has two endpoints, will be twice the number of edges, so it is 2n minus 2. But now let's look at this. We have n vertices, and the sum of all degrees is 2n minus 2. There are no vertices of degree 0. Why is that? Think about it. A tree is connected. A vertex of degree 0 means an isolated vertex. We cannot have any such vertices. So in order for the n vertices to give us this sum of degrees, now that we know that each vertex contributes with at least 1 to this sum of degrees, well, if all vertices contributed with degree 2 or higher, this will be at least 2n or higher. So in order for n vertices, each with a positive degree, to give us a sum of 2n minus 2, when we sum all the degrees, at least two vertices will have to contribute with less than 2 to the degree sum, and therefore it will contribute to 1 to the degree sum. So far we have some properties that we have seen hold in trees, and some properties seem to hold in trees. So we've already, by definition, the fact that trees are connected, they have no cycles. We just proved that the number of edges is just 1 less than the number of vertices. In the proof of the theorem, we saw that removing each edge, or removing any edge rather, disconnects the tree. So this means that any edge is a bridge. Remember, a bridge is an edge whose removal disconnects the graph in question. In other words, it's a cut set of size 1. There are other properties that we haven't proved, but you might perhaps believe in them. If you look at a tree, it seems like between any two vertices, well, there's at least one path because the tree is connected, but there is no more than one path. There's exactly one path between any two distinct vertices. So distinct here is important. And also, it seems that whenever we add an edge, we create a cycle. So if we have this tree, and we add an edge, then we create a cycle. These properties will be used in some combinations to characterize trees. So we'll have several alternative definitions of trees, namely as follows. So if you have a graph T with n vertices, then the following statements are equivalent, meaning that either of these statements is equivalent to any of the other statements. The first statement is that T is a tree, meaning that T is connected and has no cycles. It is equivalent to say that T has no cycles and has precisely n-1 edges. Remember, n is the number of vertices. Another statement, T is connected and has precisely n-1 edges. Further on, T is connected and each edge is a bridge, meaning that removing it will disconnect the tree, or the graph, rather. We're not assuming that it's a tree, except for in number 1. Number 5 is T has no loops, and any two distinct vertices are connected by precisely one path. And finally, T has no cycles, and adding any edge creates precisely one cycle. So this means that each of these statements can be used as a definition of a tree. Why is this useful? Why do we need so many ways to say exactly the same thing? Well, in different situations, different properties are easier or harder to check. Remember when we defined connectedness, we had this definition that you cannot write the graph as a union of two graphs, but sometimes that's hard to check. It's easier to check the equivalent statement that you can draw a path between any two vertices. Similar here, if you want to check that something is a tree, now you can check any one of these 6 statements that you like, and that's easier in that context. Now our task is to prove this theorem. So we need to prove that each of these statements is equivalent to all the other statements. The quickest way to do it is to prove that statement number 1 implies statement number 2, implies number 3, implies number 4, implies number 5, implies number 6, implies number 1 back. You might have seen this in other courses, but this implies, for example, that 5 and 1 are equivalent because 5 implies 1 and 1 implies 5. So you prove this cycle of implications, as it were, to prove the theorem. And this is what we are going to do now.